If you took about 2,000 television antennae, connected them all together, plugged them into a very good amplifier, receiver, and pointed them at a particular part of the sky, you might hear something like this. Perhaps sounds to you like a truck or a tractor, a rather roughly running truck or tractor. It's not, actually. What you're hearing is a star that's about 10 miles across, spinning. Each of those beats corresponds to one spin of the star. Have another listen. You're listening to a pulsar, or a neutron star. I'll probably use those two terms interchangeably this evening. They're almost the same, and for the purposes of this evening's talk, let's just take them as two versions of the same thing. You're listening to one of the most bizarre kinds of objects that there is in the universe. Something that seemed quite incredible, hard to believe at the time we stumbled over them. And if you stop to think too hard about them these days, still seem equally incredible, frankly. But before I launch into a detailed discussion about these things, let me start by showing you some slides to set the scene. To begin with, it's just a geography lesson. Geography of the universe, the cosmos. And we start fairly near home with a planet. Actually, the planet Saturn with its beautiful rings. Saturn, like the Earth, is one of the planets that orbit the Sun. Could we have the next one, please? Here the Sun fills almost the whole of the screen. It's the round yellow ball. The black specks are not dirt, they are actually on the Sun. Those are sunspots. One of those sunspots, let's for instance take this one, is probably bigger than planet Earth. If you put the Earth up beside it, you'd see that the sunspot was bigger. Sunspots look dark because they're a little cooler than the rest of the Sun. They're not actually dark of themselves, they're quite bright. They're not as bright as the rest of the Sun, though, so they look dark to us. They've got an interesting history, these sunspots. They were observed by the Chinese, the ancient Chinese. In ancient China, any emperor worth his salt had a court astrologer, and I do mean astrologer. It was the astrologer's job to watch the skies, to observe conjunctions of the planets and eclipses of the moon and strange new stars and anything like that. And the astrologer not only had to observe these things, but he had to divine what they were saying. And he had then to advise his emperor about whether it was the right time to make war on his neighbor or pinch the neighbor's chickens or whatever the latest scheme was. The ancient Chinese observed these sunspots but failed to pass the information on. And they were rediscovered in the Middle Ages by the Italian Galileo Galilei. This was one of the reasons for Galileo's problems with the church, because Galileo, as indeed many a scientist today would say, "Ooh, look, there's spots on the sun." And the church, without looking, said, "Oh no, there ain't. The sun is a heavenly body and therefore is made of perfect fire. There are no spots on the sun. Go get your eyes tested, Galileo Galilei." Well, there were spots on the sun, and there are spots on the sun from time to time, and that shows you some of them. Could I have the next slide, please? The sun is a star, an exceptionally ordinary star, bog standard, common or garden. And it just looks different to us compared with the other stars because it's so very close. There are many, many other stars in the sky, and on the screen at the moment we have a group, a cluster of stars. They come in various sizes, brightnesses, as you can see, and maybe you can also see sometimes they have a hint of colour. I'll come back to the colour question shortly. There are probably hundreds or maybe even 1,000 stars on that particular image. The next slide, please, shows a galaxy, which is a group of about 100,000 million stars. We live inside one such galaxy. We call it the Milky Way. There are a number of them spotted all over the cosmos, and each of them is this almost self-contained group of stars. In the center, the stars are fairly closely packed, and on this grain of photograph, you can't separate them out. It looks a solid blur of light. The inner parts of a galaxy do tend to be a reddish-orange color, compared with the outer parts, which are bluer. And on this slide, you can see some of the beautiful spiral arms, or these curling lanes of gas and stars. Tend to be younger stars in these spiral arms. If we could get outside our galaxy, it would look something like that. And our sun is just one of those 100,000 million stars. And it's not even in the center. It's somewhere out about 2/3 of the way out. A very ordinary star in a very ordinary place. And the next slide, please. The galaxies are groupings of stars, and we now know that the galaxies themselves are grouped into clusters. And this shows part of a cluster of galaxies. There's a galaxy down there, that's rather a famous one. Beautiful open spiral arms. That's a galaxy, so's that, and that, and that, and that, and that, and those two, and that, and that, and that, and probably many more on the slide if I looked more closely. There's probably several thousand galaxies grouped together in that cluster, and there are many clusters in the sky. There's a very handy multiplication table produced by a British scientist, an astrophysicist called Eddington, which gives you a rule of thumb about how many stars and so on there are in the universe. The multiplication table only has 2 lines, so it's not that onerous, but the numbers are pretty big. And it goes 100,000 million stars equals 1 galaxy, 100,000 million galaxies equals 1 universe. So there are plenty of stars and plenty of galaxies in the universe. Could I have a little more light for a moment? And then I'll go back to the slides. Lovely. That's the geography, the Cook's tour of the cosmos, the layout. What I want to talk about next is the birth and life and death of stars, because that's relevant to these pulsars or neutron stars. I'm going to start by showing you that I'm mad. You discover this anyway sooner or later, so let's get it over with sooner. This is stellar evolution in about 2 minutes. There's a whole lot of particles of gas and dust milling around in one of the black bits of the galaxy. And by a quirk of nature, some of these particles of gas and dust cluster and form a knot. And the knot has extra gravity, and so it pulls in more particles of gas and dust. And they gradually coagulate. And there's more gravity, so more gas and dust gets pulled in. And it forms a ball that gets tighter and tighter. In the center of this ball, the material is getting quite hot and bothered, because there's all this other stuff piling in on top of it. And its temperature goes up. And when the temperature in the middle reaches about 10 million degrees, you start getting a sort of burning. It's called nuclear fusion. And that's what makes the star shine and give out heat. So the star sits there burning. Now this can't go on forever because it is a burning and fuel is getting used up. So after a while, it begins to falter. Boom! And the stuff gets all spread out in a giant explosion. And gas and dust and metals and things fly out into space. And somewhere over here, some of these particles of gas and dust come floating over and join with some others and form a little knot that has gravity, that pulls in more material, that forms a ball that gets tighter and tighter, and the temperature in the middle goes up. Boom! And off we go again. Should perhaps say that not all Brits behave like that. I only know of one other, and that's the bloke I pinched the mime from. Yes. Right, could we go back to the slides? Could I have the lights down a bit, please? And could I have the next slide? This is now the authentic version of what I've just been talking about. This is one of the dark bits in our galaxy. It's the famous Horsehead Nebula in the constellation of Orion, which looks like a horse's head. What is actually happening is that some of the dark material down here has got scooshed up, and we're seeing it silhouetted against some brighter, glowing hydrogen gas. There's also dark lanes of material in this nebula, and it's in places like this, those dark lanes, that the new stars form, that stars are born. So if you like, there's a stellar nursery in there. It remains black for some time, and we can't see it unless we use some of the special telescopes that work at millimeter or infrared wavelengths. But in those dark bands, there is this coagulation going on and stars being formed. Stars are actually born and live and die just like human beings, but they take a lot longer over it. The sun, for instance, has been burning for about 5,000 million years and will go on for another 5,000 million years or so. But it will die one day, as will any star. Go to the next slide, please. This is a group of young stars, which a number of you may be familiar with. It's the group called the Seven Sisters, or the Pleiades. And you can see it in the winter sky. You find it by identifying Orion and tracking up Orion's belt, and you come to this little group of stars. It's a very good group of stars for testing your eyesight on. How many can you see? This photograph's taken with a telescope and of course shows a lot of stars. With the naked eye, maybe you'll see the 7 that the ancients saw, or if your eyesight is like mine, maybe you'll only see 4 or 5. But this is a group of relatively young stars. That's to say they've formed relatively recently. They're now big and bright and blue, and probably won't last that long either. They're a kind of star that's going to tramp through its life quite quickly. The next slide, please. This is another of these groups of stars. It's known as the jewel box, this group, because it's got several coloured stars in it. There's one that's, I think, fairly clearly orange there. That one has a pink tinge, that one has a pink tinge, and that one has a pink tinge. Maybe so does that one too, with a bit of faith. Now, it's a bit of a sweeping generalization, but it's quite a good rule of thumb. If a star is looking pink or red, it may be that it's through its middle age and it's beginning to show signs of senility. When the sun runs out of fuel in its center, another 5,000 million years hence, the sun will go red. It will also swell. It will swell to engulf the planet Venus. It will have already engulfed Mercury. And whether or not it swells to engulf the planet Earth is a little bit iffy. But it doesn't actually matter, because if a stellar surface at a temperature of a few thousand degrees comes this close, we're charred. The Earth becomes a cinder. So in 5,000 million years' time or so, the Earth will become uninhabitable because the sun is dying, and dying in a dramatic way. And we, if there's still Homo sapiens on the Earth, will have to be very intelligent and build ourselves some spaceships and go find somewhere else to live. We can't stay here forever. So the sun does this swelling act, and it's not going to boom at the end of its life because it's not a very massive star, but bigger stars do boom in a most dramatic way. Could I have the next slide, please? You'll see in the bottom right-hand corner of this slide that an arrow has been conveniently placed. It's not there on the sky, it should be said, it's only on the slide. This is a slide of a nearby galaxy which you can see from the southern hemisphere. It's called the Large Magellanic Cloud. It contains lots and lots and lots of stars and a certain amount of this pink stuff which is hydrogen gas. And one particular inconspicuous star has been picked out because, if we go to the next slide, thank you, that's the star that was picked out. It exploded dramatically and was observed to explode in February of 1987, early 1987. This is something that astronomers have longed for generations, because there hasn't been one of these that was readily observable since we invented the telescope for hundreds of years. And it's important to observe one of these booming, exploding stars because it lets us check out a lot of our theories of astrophysics. And I must say, with one possible exception, the theories of astrophysics checked out really well. That booming star has been observed and followed in the, 7, 8, getting on for 9 years since, and lovely, excellent. In this boom, a lot of the material is kicked off into space, but some bit of it remains. And the bit that remains was the bit that was in the middle of the star, the core. And in the explosion, the core of the star gets kicked against. It gets compressed, very compressed. And that becomes a neutron star or a pulsar. So these exploding stars are important for tonight's story because, contrary to expectations, the star doesn't completely destruct. It remains a core that produces some very bizarre behavior. Could I have the next slide, please? About 1,000 years on, an exploded star looks a bit like this. There's a sort of mess of gas that's still glowing. And the core of the star is actually that one, which perhaps the front row can see, but I guess folks at the back will have to take my word for it. There are a pair of stellar images there, and the bottom right-hand one is believed to be the core of the star that exploded and is now known to be one of these pulsars. And the next slide, please. And many, many thousands of years on, it'll look perhaps like this. This wispy stuff is the tentacles of gas left over from the explosion. This particular debris is the remains of the explosion that created the pulsar that you listened to a minute or two ago. So somewhere down here, which is about the center of some of this stuff, there is a star that's spinning about 11 times a second and going tuk, 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 like you heard on the tape recording. Right, I'm going to pause the slides there. Could we have a bit more light for a moment? And I'll come back to the remaining slides shortly. I mentioned that the star was highly compressed. If I were to take the cap of a pen, any pen, and fill it full of neutron star material, pulsar material, it would weigh about 100 million tons. They're very heavy. They're very small, very compact, with some very interesting physics inside them because they are so small and so compact. It was this compactness that we didn't initially appreciate and caused us such great problems when we were trying to disentangle these things when we first discovered them. As Paul Vanden Bout has mentioned, what I was doing was working for my doctoral thesis, and the task was to study quasars. Quasars would be another lecture in themselves, and I won't say too much about them, except to say that they are some of the most distant things in the universe, and still some of the most puzzling. They're incredibly bright, and yet we can see them in the furthest reaches. By late 1967, they'd been recognized for a few years for what they were. And it was realized that if you wanted to study the early universe, as well as studying the quasars themselves, studying quasars was a good way to do it. And my particular job was to identify all the quasars that could be seen in the sky from Cambridge, England, and through a rather complicated twinkling mechanism, work out how big they were. You know that if you look over a bonfire or over a barbecue, you see things shimmering. It's the heat from the barbecue or the bonfire that does it. There's a similar phenomenon in radio astronomy that's called scintillation or twinkling. Coming off from the sun, there is heat, but there is also gas, plasma, streaming out into space. And this plasma makes the radio signal shimmer or twinkle. And it does it particularly for very compact things like quasars. So it looked like a very good way to pick out the quasars and to measure their size. Because it's a phenomenon that originates in the sun, it tends to happen when the quasars are in the daytime sky and not when they're in the nighttime sky. Well, I spent about 2 years actually physically building the radio telescope. I became very adept at using tools and swinging sledgehammers and things like that. Highly academic work. But I must admit, an ability to use 2 pairs of pliers and untwist bits of wire or twist them up has had some uses in later life. And then after 2 years of building, we started operating the telescope, and it was my job as the grad student to operate the telescope. We didn't listen to the radio signal. I mean, I've started by playing you an audio recording, but in actual fact, radio astronomers don't work with headphones on. You work with some more permanent record than that. These days it's computer tape, but in those days computer power was very limited and not for projects like mine, so our output came on paper chart. 100 foot of paper chart every day, which yours truly had the job of analysing. There was a funny signal occasionally Well, there were lots of funny signals. They were called arc welders and taxi radios and aircraft altimeters and badly suppressed cars and, things like that. But one got to recognize that interference. There was another funny signal, and it was in the middle of the night, which was very peculiar, which we couldn't place. Couldn't immediately follow it up either because we still hadn't finished commissioning the telescope. We were still waiting for more pen recorders to arrive and this kind of thing. We were operating, but barely operating. But once we got our full complement of receivers, I set to study this peculiar signal. And by that time, the peculiar signal wasn't cooperating. The peculiar signal had disappeared, just wasn't there. And my thesis advisor got terribly upset and said, "Oh, it's a flare star, it's been and gone and done it, and you've missed it." Grad students are very useful. They take the stick for all sorts of things, as you probably know. And after a month of failing to observe this wretched thing, I skipped one day going out to the observatory, and it reappeared. I got it the next day, and it came out as a string of pulses, equally spaced pulses or flashes, about 1 1/3 seconds apart. We were observing with an instrument which was fixed in the ground, and it depended on the rotation of the Earth to sweep through the sky. And once the bit of sky you were interested in had been turned away from the telescope beam by the rotation of the Earth, there was nothing you could do. So after seeing a few minutes worth of pulses, I was, so to speak, left with egg on my face. What would I do now? Well, I phoned my thesis advisor, who was teaching back in central Cambridge. He was teaching in an undergraduate physics laboratory, and I believe he had just been handling one not so academically intelligent Cambridge undergraduate who thought his diffraction grating had 3 lines per inch, when his perhaps not terribly intelligent grad student phones him up from the observatory and says, "You know that piece of scruff? It's a string of pulses, 1 1/3 seconds apart." Well, thesis advisors are there to moderate students' enthusiasm, so he said, "Oh, well, that settles it, it's man-made." I think he reckoned it was some kind of interference, radios, radars, altimeters, arc welders, something like that. I wasn't quite so sure. I think that was partly ignorance. This thing was pulsing at 1 1/3 seconds, which is really quite fast. It's also the kind of frequency that you might set a signal generator at, so it could be man-made. But what I hadn't appreciated was that stars are big things, like elephants. And this thing is behaving like a flea. Elephants can't turn round in 1 1/3 seconds, or normal stars can't turn themselves around in 1 1/3 seconds. It had to be something small. I think the other thing that I had appreciated but couldn't properly articulate at that point was that this thing was moving round with the stars. It was keeping place amongst the stars. So I wasn't totally convinced that it was man-made, but in a sense that was Tony Hewish's problem and not mine. Tony was interested enough to come out to the observatory next day at the time when that patch of sky was turned into the telescope beam. And I realize now how very lucky I was, because pulsars rarely perform to order, but this one did it for a second day running, and in came a string of pulses, 1 1/3 seconds apart. And that's where the trouble began. It's all very well discovering something unexpected, but it's actually quite a headache, because you have to convince yourself that it's real and that it's not something instrumental. There's a very great danger in astronomy where you're dealing with these great cosmic things, that you fall into a trap of what Phil Williams described to us young postgrads as folie de grandeur. You see something and you assume it has immense cosmic significance. and it's actually your equipment misbehaving. So you have, any scientist has to be careful. But I think particularly when you're dealing with universal and cosmic things, you have to be particularly careful because you can get carried away. So we spent a long time convincing ourselves that this thing did go round with the stars, that it wasn't local interference, that it wasn't this, that it wasn't that it wasn't radar signals bouncing off the moon and into our telescope, that it wasn't a satellite in a funny orbit, and so on and so forth. But we had a very great problem. This thing kept pulsing at 1 1/3 seconds. Very, very, very precisely. It showed no signs of flagging. It wasn't getting tired. Now, for something to keep going that regularly, day in, day out, week out, suggests that it's got very great energy reserves. And if it's got very great energy reserves, that means it's big. But it's small because it's going every 1 1/3 seconds. And that was the conundrum that we couldn't solve. It's big and it's small. Well, we now, with hindsight, our best developed faculty, as they say, with hindsight, we can see that it was big in the sense that it was massive, but it was small in the sense that it was physically small. So it was a big mass in a small size, a small volume. It was very compact or very dense. We were still a bit hung up on this idea about it being man-made interference. Could we go back to the slides, please? And yes, lovely, thank you. An original record, only slightly doctored. This is some of the chart recording. And there are 3 traces on it. The bottom trace is time signals, 1 second time pips. That is man-made. Comes from a radio station in the centre of England. The trace above is this pulsar. It goes blip, 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 misses one, I think, blip, 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 misses several, and then a few more. And we nicknamed it LGM1, Little Green Men 1. It was strictly a joke, and that terminology is now suppressed, so you haven't seen it. But we did for a while, half in jest, entertain the idea that, well, if there are little green men out there trying to signal to planet Earth, it's going to be the radio astronomers who pick it up first. We got to the stage where we had studied LGM1. We had established that it was going round with the stars, that it was some distance away, it was beyond the sun, the planets, but it was well within our own galaxy. We wondered whether it could be little green men and set up a test to check it. We live on a planet that goes round the sun. If there are little green men in the universe, they probably live on a planet that goes round their sun. We thought we might be able to detect the motion of their planet round their sun by timing these pulses very accurately. Because when the little green men's planet was coming towards you, towards us, the pulses would be piled up together, and when it was on that bit of the orbit that took it so it was moving away, the pulses would be stretched out. So we set up this timing program to look for this orbital motion, and we found an orbital motion. But it was the motion of the Earth round the sun. So we established that the Earth goes round the sun, but couldn't see any other motion. We got to the stage of wondering how we were going to announce this, what we were going to do. We still only had this one object. It seemed to be unique. We didn't have a good physical explanation for it. We didn't really think it was little green men, but we couldn't say we believe it's a hooji flip and, you know, handle it properly. That night, I went back home from the laboratory feeling very disgusted. Why does some little lot of little green men have to pick my telescope and my frequency to signal to planet Earth when I'm trying to get a doctoral thesis out of all this? While all this was going on, the telescope was still churning out 100 feet of chart paper every day. And the rolls of chart paper, the unanalyzed rolls of chart paper, were piling up on my desk. Came back into work that evening to deal with some of this backlog, and whilst examining a totally different bit of the sky, and for the radio astronomers in the audience, it was Cassiopeia lower culmination, because in Britain, Cassiopeia never sets. In a completely different part of the sky, there was some of this scruffy-looking signal again. That bit of the sky was due to go through the telescope beam in the early hours of the morning. So in the early hours of the morning, and it was about the 20th of December by then, and distinctly cool, I went out to the observatory. When it was cold, the equipment didn't always behave properly. And when I got there at about 2:30 or 3 in the morning, the equipment was not behaving properly. I swore at it. I applied pressure with the foot. I breathed on it. I flicked switches. And I got it to work for 5 minutes on the right setting. And in came blip, 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 blip. 1¼ seconds apart. Well, that scotched the little green men theory. There are unlikely to be 2 lots of little green men in opposite parts of the universe, both deciding to signal to inconspicuous planet Earth at the same time with a technique that is technologically not the best. It had to be some kind of star. And shortly after Christmas, I found the 3rd and the 4th. And we still weren't too sure what the stars were, but they had to be some totally new kind of star. And frankly, that's a lot better than finding little green men. There was plenty of press, hooey as it was. If it had been little green men, I don't know where we'd have got to. Now there are about 700 of these things known, and they all send out radio pulses. Most of them are faster than the ones I observed. Typically they spin about twice a second. They pulse about twice a second. Some of them go several hundred times a second. They're quite amazing. In the 25 or 30 years since they've been discovered, we've not only found more of them, but we've gained in understanding. But we are still not very clear how or why we get this radio pulse. We believe that for some reason, you get a beam of radio waves coming off this star. And as the star spins, the beam sweeps round. So it's a bit like this with this flashlight. As it spins, the beam sweeps round. And you see a pulse each time the beam sweeps across you. We get a radio pulse each time the pulsar beam sweeps across the Earth. It's a bit like a lighthouse, sweeping round, being spun round with the star. So this does mean that these stars, these whole stars, are spinning round several times a second, up to several hundred times a second. Quite phenomenal. Could I have a bit more light, please, for a minute? I'm going to pass something around, some envelopes, and ask you to take one of whatever's in the envelope. It's not Halloween candy, so don't get excited. And so as I don't create a ghastly accident, I'm going to have to unplug a microphone. Please take one of these things and pass the envelope on. the envelopes are going round, I'll say a little bit more about the nature of these objects. The real problem is to believe them, I must admit. I've mentioned that they were formed in these exploding stars, as the cores of the exploding stars. They're very small and they're very dense. There's something like 1,000 million tons of stuff squeezed into a ball about 10 miles across. The mass of the sun compressed into a ball about 10 miles across. The densities are remarkable, comparable to the density you find in the nucleus of the atom. They've also got very strong gravity. I don't suppose many of you have climbed Everest, but you can probably imagine how much work it would be to climb Everest. The gravity on a neutron star is so strong that if there was a mountain about ½ an inch high, the work you'd do climbing that on the neutron star against its gravity is comparable to the work you do climbing Everest here on Earth. There's also a very large gradient of gravity. This means that the gravitational force on your feet is much, much stronger than the gravitational force on your head. Dangerously so. If you were to visit a neutron star, as you came into land, the extra gravity on your feet would actually rip your body apart. And even if you curled up in a bundle and made yourself as small as possible, the extra gravity on the lower part of your body. So don't buy a trip to a neutron star. It's not advised. They've also got very strong magnetic fields. Here on Earth, there's a magnetic field that makes the compass point due north. The magnetic field on a neutron star is about 1 million times stronger and does all sorts of interesting physics as a consequence. The whole thing is spinning very fast. Could I have the next slide? This is really technical. In case you don't want to follow this, let me just say I'm going to be talking about what the inside of a neutron star is like for a few minutes. And as a very rough guide, the inside of a neutron star is like a raw egg. There's a shell, a solid shell on the outside, and some peculiar gooey liquids inside. That's the first cut. Here's a slightly more technical cut. And this is one of the areas where there has been great progress in the last 25 years or so. Most stars are balls of burning gas, but a neutron star does have a solid shell, really solid. It's made of iron, and it's very tightly packed iron into a polymer form, and it's about 1 million times stronger than steel. So it's fairly rigidly encased. Inside that iron crust, there's a layer where there are neutron-rich nuclei. These are nuclei that here on Earth would be radioactive, unstable, would decay. But in a neutron star, the decay is forbidden, inhibited. And so you find very exotic nuclei, very far away from the line of stability. Inside that is a superfluid layer. Now, a superfluid, it's not something that gives you more miles to the gallon in your auto. It's a technical phrase. A superfluid is a fluid that has got no resistance to flow. So if, for example, the Atlantic were made of superfluid, it would be one of the Earth's greatest resources if it were. But quite apart from that, we'd probably all travel by sea. Because if the Atlantic were made of superfluid, you could take a bathtub or some sort of box, set it in the sea, just off the coast of the USA, give it a gentle tap, and it would glide across to wherever, Europe, because there's no resistance to flow. It will move without effort. Well, the Earth isn't like that, but there is some inside a neutron star. And incidentally, having that kind of stuff inside a star that's spinning several times a second, 10 or 100 times a second, Really makes life quite entertaining. The core of the star we do not properly yet understand because the nuclear and particle physicists have not yet got big enough machines. The material here is extremely closely packed, and the only way we get information on how material behaves at these close packings is in these accelerators, where particles are flung at each other with great energy and temporarily get extremely close. We're not sure whether the center is solid or liquid, or whether there's some of one and some of another. We're not quite sure what they're made of. A friend of mine describes the center of a neutron star as a rich Greek alphabet soup. And for those of you who are into particle physics, that just about summarizes it. We don't know, really. But it's exotic, whatever it is. I've mentioned that the pulsars kept very good time. They didn't show any sign of flagging. Just went on pulsing ever so accurately. We've used this, various people, to do other tests, other experiments. Quite a lot of stars in the universe are paired. The two stars dance around each other, orbit around each other, and they're held in a pair by gravity. If one of this pair of stars is a pulsar, you can check out gravity, and it works like this. It's a very sophisticated experiment. It involves my kitchen timer, brought all the way from Britain, and some really elaborate stuff. It is slightly risky. The nearest inhabitants have about half a second to duck if this comes adrift. Listen to a pulsar in orbit around another star. That's it stationary. You study the timing, the arrival of the pulses, and you can get the orbit of the pulsar around the companion star. And you can use that to check out the gravitational forces. And I'm sure you're terribly anxious to know that gravity's good to 1 part in 10,000 million. And if we go on doing that experiment for about another 10 years, we're probably going to show that gravity is good to 1 part in a million. It does show you that these are very precise things. One of the Jansky lecturers, perhaps 5 or 6 years ago, was Joe Taylor. And he has used pulsars for a slightly different demonstration. Einstein predicted that if something is going round, or indeed being accelerated in any other way, it's going to emit a special kind of radiation called gravitational radiation. If a pair of stars, as they go round, emit gravitational radiation, that stellar system is losing energy. If a stellar system loses energy, the two stars move closer together and go round each other faster, which causes more gravitational radiation, so more energy loss, so they move closer together and go round each other faster. And the effect sounds something like this. As it loses radiation, moves in, and spins faster. Dangerous for me as well. Joe Taylor has tracked one particular pulsar for about 20 years with great accuracy and shown that it is behaving like that, and that furthermore it's behaving in a way that exactly confirms what Einstein predicted. So he's been checking out Einstein's theory of general relativity on gravitation, and it does check out extremely well. I'm going to move now to the overhead. That's all for the slides. Thank you very much. Just remind you of a little bit that I've been saying, and then finish with some slightly more startling stuff. We believe that pulsars are formed in these supernovae explosions, that they're the cores of the exploding stars. They're highly compressed objects, this 100,000 million, I've lost track, you can read it, million tons in a 10-mile ball. That they are made largely of neutrons, not entirely, but largely. So they're called neutron stars as well as pulsars. The 700 that we know are spread throughout our galaxy. Well, not throughout, they tend to be in the nearer half because, as you will have gathered, they're quite weak signals. But we believe that in general, pulsars are scattered throughout our galaxy and presumably through other galaxies also. They are pulsating radio stars. Pulsar is an abbreviation for pulsating radio star, producing regular pulses of radio waves, that they're spinning fast and they have a strong magnetic field, and somehow out of this comes something like a lighthouse beam, a radio beam that spins round. They are very accurate timekeepers. I think I perhaps forgot to mention a figure. The typical pulsar is accurate to 1/3 of a microsecond per century. They are spinning several hundred times per second, some of them, the slower ones to once every few seconds. I did a little bit of work for the Guinness Book of Records. Do you have that here? Yep, right. Some pulsar facts from the Guinness Book of Records. The fastest known pulsar is that one, with a period of that number of thousandths of a second, with a little bit of uncertainty, but not too much. They are, in fact, phenomenally good timekeepers. They're better than a quartz watch. And the best ones have a jitter, and this is a fractional jitter, of only that. The most accurate timekeeping pulsars seem to be more accurate than the world's best time standards. And I think we're shortly going to be in the situation where we use the pulsars to time our time standards, rather than the other way around. They will become our time standards. I think in the light of recent news, I will modify the next one slightly. The first definite planets discovered beyond the Sun and its planets are planets round a pulsar. There are 2 moderately massive planets and probably a third much lighter one around this pulsar, PSR 1257 plus 12. I can give you several very good reasons why there can't be planets round a pulsar, or there shouldn't be planets round a pulsar, but there are. There are several pulsars that are twinned with other stars in a binary system and going round them. One of these orbits is the roundest known thing in the universe. If you drop a coin or a pen or anything onto the surface of a neutron star, just from about waist height, it will hit the surface of the neutron star going at half the speed of light. 93,000 miles per second. And finally, in the center of a neutron star, the pressure is a little high. Have pity on those of us who have to believe these things. Thank you very much.
Jocelyn has agreed to answer a few questions if there are.
Try
Yes.
to.
Starquakes. I seem to remember reading about those some time ago.
Yes.
Is that what confirms the notion that the outside is crystalline iron or something? Or have they gone away?
No, they've not gone away. They've got more present. To fill in for those who may not realize what we're talking about, I've mentioned how accurate these pulsars are, and that's true for most of them, but there's one or two that occasionally hiccup or glitch. I've discovered that glitch is a Yiddish word meaning to slip. And what happens is the pulsar is quietly pulsing away and then suddenly goes and settles down again. And one suggestion was that there had been an earthquake on the star, a star quake. There was a thought that maybe this very rigid iron shell was readjusting its shape as the star gradually settled into middle age. But that theory's not going to work. It doesn't hold water when you study these glitches. Then they wondered if there was an earthquake in the core, if the core were solid, and they worried about that for a while and decided that wasn't going to work either. So they have come up with an horrendously awful picture of vortices in the superfluid normally gradually migrating, but occasionally migrating en bloc and causing a change in the pulsation. Starquakes would be simpler, but they don't actually seem to fit the data. The way the pulsar recovers after this speeding up, however, does establish that there's superfluid inside the neutron star. So they are useful for that.
Yes.
How was the structure of the neutron star determined?
Determined is an interesting word. Nobody has been there. We have not sent a geologist with their hammer. The superfluid content has been established from studying these glitches. The rest of it, I think it's fair to say, is pure theory, except it's fairly self-consistent theory, and so far is holding together. But in astronomy, sometimes these things, these packs of cards collapse, so who knows?
Yes.
If a pulsar is so very close to being spherically symmetric, is anything known about what breaks the symmetry and gives you a radio beacon in a preferred direction?
Yes, well, known again is perhaps the dubious word. The star is spinning, and let's say that it's spinning about an axis that's straight up and down, so North Pole and South Pole. It's also got a magnetic field, and we think the magnetic field is inclined. This happens in the Earth. You know that the North Magnetic Pole is actually in North Canada, not at the North Pole. Similarly, in a neutron star, only more so. And so the magnetic field spins round, or the magnetic axis spins round like this as the whole star spins. And that's believed to be what's happening.
Yes.
What is the narrowest beam of pulsar that's known? I mean, the fraction of the period which is in the pulse.
It's a few percent, the duty cycle. But it does depend at what frequency you look at it. It tends to be rather different at different frequencies. And a related point is that we suspect we're only seeing about 1 in 5 of all the pulsars, because for some of them, the beam doesn't sweep across Earth, it goes round like this. So about 20% we think we see.
Yes?
Yeah, I was wondering about the frequency where you observe the signal. Do they all have the same spectrum, or if not, is there any significance?
Most of them are only seen as radio objects. The very recently formed ones like the Crab Nebula that's 1,000 years old, we also see at higher frequencies, optical and X-ray. But it seems that once they're more than a few thousand years old, they retreat back to being just radio objects. Within the radio regime, they have a broadband spectrum that's fairly steep and doesn't seem to contain features.
Okay, thank you. Let me make the following announcement. There is a reception that begins immediately at NRAO. You're all invited to it.